Okay, so for this first example, we are just looking for an expression for the differential of y, or dy. So we have the function y equals sine of this polynomial. We are just looking for dy. And remember that dy is equal to f prime of x times dx. So for this question, all I am doing is taking the derivative and multiplying by dx. Okay, so dy is equal to, and then using the chain rule because we have a composition, cosine of x to the fourth minus 3x squared plus 12 times the derivative of the inside, or u prime, which is 4x cubed minus 6x plus 0, okay? But then we have times dx. This is exactly the same as writing dy over dx, but then multiplying both sides by dx to move that over, okay? So if you're asked to find an expression for the differential, that is all you have to do. Take the derivative and stick a dx behind it. All right, now, that's not super useful unless you can use it to answer some question. So that's what we're going to do on this next one. Okay, so here we have the function y equals root x squared plus x plus 3. Part A says to approximate the change in y as x increases from 2 to 2.1. And then we're going to find delta y and compare. See how close our approximation is. Okay, so we're going to label some pieces. We know what our function is. We've got our f of x right here. Okay, we also need to know what is delta x, and delta x is the change, and pay attention to the order because it could be negative depending if your second point is to the left or to the right of your original point. So if we are going from 2 to 2.1, TO 2.1, then that means that delta x is 0.1, and this is the same thing as dx. It doesn't matter which label you use because again they're exactly the same. Okay, so the change in x is 0.1. Okay, so now we need to approximate the change in y. Approximate the change in y, this means find dy. Okay, so we're going to do what we did up above, but we're going to plug numbers in for that. Okay, so dy is going to be the derivative of this, so 1/2 times x squared plus x plus 3 to the negative 1/2 times derivative of the inside, which is 2x plus 1 times dx. And now we are going to evaluate this, okay? We're going to evaluate this at x equals 2, the original point, or in other words, the x sub 0 point, okay? This one is x sub 0, okay? And then dx will plug in 0.1 for that, all right? So f prime of 2 times dx, which is 0.1, right, that's times, that's a decimal, okay, is going to be equal to 1/2 times 2 squared plus 2 plus 3 to the negative 1/2. You can move that down or later, it doesn't matter, times 2 times 2 plus 1 times dx, which is 0.1. Okay, and now we just need to do some arithmetic. All right, so we've got a 1/2. I'm going to go ahead and move that down. So we have times 1 over the square root of 9, which is 3, and then times 5, and then 0.1 is 1/10. And multiplying all these together, let's cancel that out. We have 1 over 2 times 3 times 2, which is 12. Okay, so our approximate change is 1/12. This is the graph of that function, okay, and I wanted to go ahead and show this to you because we're looking at how close our approximation is for the second part. Okay, so according to our approximation, our dy, we found that the change in y as x increases from 2 to 2.1, which is going to be a real small amount inside here, is going to be about 1/12. All right, part B asks us to find delta y and to compare those two things. So to find delta y, what we really need to do is subtract y2 minus y1. So for part B, here's part A, okay? And then part B, we need to find delta y, which is going to be y2, which is f of 2.1, minus y1, which is f of 2. And I'm going to do this on the calculator because that is the efficient way to do that. I don't want to try and plug 2.1 into that, that function, okay? So f of 2.1 minus f, or in this case y1, of 2, and I get 0.0838, etc. 0.0838 something. And then now let's compare these real quick. We'll go ahead and put 1/12 in a fraction or in a decimal to compare. 1/12 is 0.08333. So I would say that we are pretty close. Okay, let's write that down. This one is about 0.08 and then 3 repeating. Okay. Now, if a question asks you to find the error, then you need to subtract these two, but then always give the positive number. So error is equal to the absolute value of delta y minus dy. And again, it doesn't matter what order we subtract because we're going to have a positive anyway. So in this case, here, this is important. Important. Okay. So let's go ahead and find the error for this one. It's going to be, so for this one, it's going to be 0.0838 minus 0.0833, which is rounded 0.0005. So that's really close, okay? I would say that this is a good approximation using our differential to approximate the actual change, okay? Let's do another example here. This one says use differentials to approximate the increase in the surface area of a soap bubble when its radius increases from 3 to 3.025. Okay, so to start with, we need a function. Okay, and the formula for surface area of a sphere, assuming the bubble is a sphere, is 4 pi r squared. You can use y and x if you want. We are increasing from 3 to 3.025, so delta r is 0.025, okay, which is 1/40 if we want to do this without a calculator, okay? It doesn't really matter to me which way you do it. And then we also have a starting point, an r sub 0 of 3 inches, okay? So make sure that you can identify those 3 things before you start the problem. All right, so we are approximating the increase in surface area, okay? So we want to approximate delta S with ds. To find the derivative of, or the differential of S, we take the derivative of this, which is going to be 8 pi r times dr, and then we are plugging in these values. So that's 8 pi times 3 times 1/40, okay? And then we get 3 pi over 5. And since that is a change in surface area, then that is going to be units, so in this case, inches squared. And I'm not sure what that comes out to be, probably like 1.8-ish or something, but we can just stop right here. Okay, so that's the approximate change. All right, let's do one more, and then I'm going to have you do a couple on your own. So for this one, we are approximating the cube root of 8.01 without a calculator. Okay, now this one is written a little bit differently. It doesn't actually tell us what our function is, what our starting point is, what our change is, but we need to identify those. So first, let's write this as a function, and let's write it as y equals the cube root of x, or since we're taking the derivative, we can write it as x to the 1/3. And then for our starting point, let's pick something where we know its value. Well, we know the cube root of 8 is 2. That's an easy cube root, okay? So let's say that x sub 0 is equal to 2, and I'm picking, x sub 0 is equal to 8. The cube root of that is 2. And I'm picking 8 because it's close to that. Now, I could also say, well, the cube root of 27, I know what that is as well, but 27 is not close to 8.01. Okay, so I'm picking 8 for my for my starting point here, and that means that delta x is going to be 0.01, or 1/100. Fractions are better for doing things by hand, okay? All right, so we have a function, we have a starting point, and we have a delta x. Okay, so let's figure out our approximate change. So dy is equal to the derivative of this function, which is 1/3 times x to the negative 2/3 times dx. Okay, then plugging in our values, we get 1/3 times 8 to the negative 2/3 is 1 over cube root of 8 is 2 squared is 4, and then times dx, which is 1/100. Okay, multiply those and we get 1 over 1200. Now, this problem is also a little different in the final answer that it is asking for. It is not asking us for the approximate change as x increases from 8 to 8.01. It's asking for the approximate value. And the cube root of 8.01 is not 1 over 1200. Okay, it should be something that is slightly bigger than 2, right? So this is where we need to go one step further. And if we go back up here, okay, let's think about it this way. We were just approximating this part right, we were approximating this change right here. If we want to approximate the actual y value here, we need to add our approximate change to the original height. Or in other words, because we found dy, we found this vertical change, we need to take that and add it back to the original height in order to, or the original value of the function in order to approximate the total change. Okay, so for this one, f of 8.01 is approximately equal to f of 8 plus dy that we just found, okay? Or in this case, 2 plus 1 over 1200, which is 2401 over 1200. Okay. You try the last couple.